Now, I'd like to talk about the PCA method, which is the topic 12. And first, let's talk about the main method. Well, PCA is a linear dimensionality reduction technique that projects data onto a new coordinate system through orthogonal transformation. And the key idea is to find directions that maximize the variance of the projected data. These directions are called principal components, and they form an orthogonal basis that captures the most important patterns in the data. And then let's talk about the mathematical foundation. Well, PCA relies on linear algebra concepts like eigenvalues, eigenvectors, and we start by centering the data, then compute the covariance matrix. And the eigenvectors of the matrix became our principal component, where the eigenvalues represent the variance captured by each component. And well, in our Julia implementation, we use eigen decomposition to extract this component effectively. And for the implementation part, I think we better take a look at the code which is here. Well, first, we center the data by subtracting the mean, and then we compute the covariance matrix using matrix multiplication. And finally, we perform eigen duplication and sort the components by descending eigenvalues, which will give us the PC1 and PC2, which are the directions of the maximum and second maximum variance. And then let's take a look at the result, which is here. The visualization shows how variance changes with different projection angles. The peak of the purple curve identifies the optimal direction that captures the maximum variance. This exactly matches the PC1 direction shown by the red dashed line, and the perfect element demonstrates that PCA successfully finds the most informative data representation. And then for the variance analysis and optimal combinations, which are about these words, all variance analysis reveals a striking result. PC1 explains 98.6% of the total variance with eigenvalues of 4.86, which are shown here. And PC2 only explains 1.4%, and the optimal combination analysis shows that PC1's directions are nearly identical to the theoretical optimal projection, with only 0.006 radiation differences and the perfect direction similarity of 1.0. This confirms PCA successfully found the best linear representation. Well, like all methods, PCA have limitations, which will be shown here. It's primarily linear and may miss complex nonlinear relationship. However, we can overcome this with kernel methods for nonlinear transformation or use deep learning approaches for more sophisticated dimensionality reduction. This extension maintains PCA's interpretability while handling more complex data structure. And then for the application part, PCA has widespread applications. In data visualization, it helps us understand high-dimensional data by projecting it to 2D or maybe 3D while preserving the original data structure. And for the feature compression, we can replace hundreds of original features with just a few principal components, reducing storage and computational requirements while preserving essential information. And additionally, PCA serves as an effective tool for anomaly detection by identifying outliers that exhibit large deviation along minor principal components, which typically capture noise and anomalous variation rather than just the main data patterns. And now for conclusion. Well, our PCA demonstration shows how linear algebra principles enable powerful data analysis, and the method successfully identified the most informative direction in data and provide interpretable components and enable efficient data representation. And the storage performance of our synthetic data set with 98.4% variance explained by PC1, which is validate both the method and our implementation. And that is all.